So I'm here getting ready for today's class, putting some notes on the board that I want to start off with. But then I realized that I do actually write a lot more on the board than I realize. Last week I joked that the new package of white chalk that I bought would last me like 2 weeks. And as you can see, I wasn't kidding. Now, this isn't completely fair. I do have a few sticks of the white chalk in some smaller packages that I carry around. But actually, these mostly colored chalk is in these. I have like a few sticks of white chalk left over here or there. But yeah, I'm definitely, it's been about a week and, pretty much about a week. Maybe a week and a few days since I posted that video, and I'm definitely like halfway through this box. I write way too much. I don't know, but that's just interesting. I'll think I'll need to order another one of these. But anyway, let's get ready for class. We're gonna get started in about 30-40 minutes. All right, let's get started here. Let me start this recording over here. Still have a few people trickling in, but yeah. Okay. All right. Welcome back, everyone. Let me make sure that I'm seeing the chat here. Okay, all right. So I guess everyone can hear me okay? Okay. All right, so any questions before we officially begin? So I think I saw some discussion in the chat going on here if I scroll up, but yeah, so in terms of, I see people talking about pass-fail grades. I'm pretty sure that's a choice that you can make, if I'm not mistaken. The first email I saw regarding grades and pass-fail, I think you have to apply for it. So I don't think they're going to do something like across the board, just give everybody pass-fail. At least the last email I heard about it, that was not the case. I don't know if there has been an update since then. But yeah, no. In terms of, there's this other pause that will be happening at CCNY. My other class voted for me to just continue doing these videos during that and pretty much just observe the regular spring break. But of course, it's not required for you to attend. But that's my Monday, Wednesday class. They voted that way. So I don't know if you guys wanted to do the same, or have you thought about it, or? So essentially what this pause thing is going to be like, it's kind of like they're cutting your spring break into 2 chunks. So instead of getting a week straight up front, you get like There's going to be a pause where you're supposed to be getting equipment from school so that you can do the distance learning thing. And then spring break was cut down to like 3 days. And so my other class just said, just teach us as usual anyway and give us the whole week of spring break where we just have a week straight of no classes. So I don't know what you guys want to do. But my Monday, Wednesday class, we're going straight until the official spring break. But of course, everything is optional, and there's no way I'll give like a test or anything due during that time. Okay. So. Yeah, I kind of agree with just keep going with the classes, and my reasoning was, yes, you're getting a week off in 2 chunks, but still you are procrastinating some stuff, and it's kind of being crunched towards the end. And I think that overall, if most of you are okay just tuning in wherever you are during that week anyway, I don't know if you have anything better to do. You might as well just learn something earlier so you have more time for it to sink in. I think that that's actually nicer. So yeah, so my other class voted that way, and I'm fine with doing it because I have nothing better to do. I'll come in and record some lectures, and whoever wants to show up, show up. But yeah, for sure it's not going to hurt anyone if they decide not to show up at all. So don't worry about that. And if you want to miss the lecture and you're concerned about catching up, catch me in office hours. So I was hanging out in the office hours Zoom meeting room, which is a different location from this room, but I sent you guys that link like last week at some point, or maybe the beginning of this week, I forgot. But yeah, so you can have a one-on-one chat with me about any concerns. So that's it. And it seems like this class wants to do the same. So we'll just continue teaching normal, and for us, we'll take the regular spring break. So during the first spring break, as it was before, whatever dates that was in April, I won't post any lectures during that period. But before then, we're continuing as normal. In terms of the pass-fail issue, someone can double check with this, but as far as I know, it's by your choice. Meaning, you could go to the registrar's office and ask for pass-fail, and it shouldn't matter if you need the course for your major or not. They'll make an exception for this semester. Normally, you can do pass-fail for a course that's required by your major, but I think they're kind of relaxing that requirement. Again, this is just like I've been reading a lot of emails, so the last thing I heard about it was that. So, yeah. Yeah, exams, we still haven't decided on that. I mean, I kind of have my own choices that I kind of know what I want to do, to use an online proctoring service, but that's definitely the kind of thing, especially when it comes to finals, not even just an in-class test, but especially when it comes to finals, I kind of have to wait for what the department says we want to do. What I want to do is I want to use an online proctoring service. So it's when we kind of outsource proctoring the exam to another service, which basically means you'd have to have access to a webcam or from your laptop or something, so if you don't have that, you'll need it. But pretty much, someone else sits and watches you on a webcam taking an exam. Like, that's kind of what it is, essentially. Of course, there will be a little bit more details to it. They'll probably have you log into a browser where you can't actually browse anything else. But yeah, it's kind of a long-distance proctoring thing. And I believe I found a service that is willing to do it for free, so it actually won't cost any money. I believe that was one of the main concerns. Of course, the integrity of the exam is the first concern. The next concern is we don't want to implement a solution that will cost students money. But I found a company that was willing to do it for free. And so that's what I was thinking for exams. So like I said, I'll post a mock test. So I'll post that, I I guess maybe tomorrow you can work on it over the weekend to kind of judge where you are, and that's it. Because normally our test 1 would have been this week, covering everything up to what we covered so far, so I'll do that. Yeah, so I think you just write it on a piece of paper, and you're either going to send pictures or you're going to scan it. So I'll definitely send you guys more details, but so far I can't really implement it without being sanctioned by the math department. So either the math department has to agree that this is something that we're all going to do, or I have to get special permission from the chair herself about this. But as you can imagine, the chair of the math department is actually pretty swamped right now, so I'm waiting a little bit to ask her. Let's actually just jump in. It's been a few minutes. But yeah, in the meantime, let's just get into this. I'll still stay back for a little bit of Q&A towards the end of the lecture in case some of you have some more concerns. But let's actually just get into the meat of the matter. So, last time we spoke about something called the Taylor series of a function. If we could infinitely differentiate a function, which we can't do that with all functions, we could create something that's called the Taylor series for a function. Now, this is just a series in one sense, it's thought of as a function, but in another sense, it's just another series, which means you can do series convergence tests on it. You can tell where it's going to work, and that is something that's called the interval of convergence. It will tell you what set of x values are you allowed to plug into this. But we also learned that this is a power series. It's always convergent. At minimum, it's convergent for the x value x equals x naught only, but it's possible for it to converge for all x's, or to converge for all x's in some window called the interval of convergence. Now, we also saw last time that, and that's what I wrote down here, if we look at the partial sums of a Taylor series, it is what we call the Taylor polynomial, and that's p sub n. Now, the rest of the Taylor series is called the remainder term, and the idea is we can think of x as its Taylor series, provided that the remainder term approaches 0 as n approaches infinity. And in that case, basically what we can do is we can think of f as its Taylor series. There will be no difference between the function and this series at all, whatsoever. Whatever you can do with the function, you can do with the series. And we'll do some examples of that a little bit later today. So, as long as the remainder term of your Taylor series approaches 0, now, there's something called Taylor's inequality, which we omitted it from the syllabus technically, but I just wrote it down here just for you to see what it would look like. It's very similar to when we were... I think someone needs to be muted. Okay, so it's very similar to when we wanted to find what was that thing? When we were doing Simpson's rule and trapezoid rule and we wanted to bound the error term, the n plus first derivative, if you can find a number that is always smaller than or equal to in magnitude, you can plug that number into this formula, and that is going to be an upper bound for your remainder term. This here is called Taylor's inequality. It's theorem 24 from your textbook in section 10.10, I want to say. And yeah, so technically we skip this formula, you don't need to know it, but I just thought I'd write it down for you to see what it looks like. And as long as this is true for all x in the interval of convergence, your remainder term is bounded above by this guy. So if this guy approaches 0, that guy will approach 0, and in that case, we can think of f as being equal to its Taylor series. Then we kind of moved on to some applications, which I left you with an example to deal with. Integration was an application. We could use series to integrate things that we can't integrate any other way, but series provided a way for us to integrate it. Now, if we can't find a nice, what's called closed form answer, meaning a finite answer, an answer with a finite number of terms, we can find a series answer to the integral. And what we can do is we can just approximate that series using some of the techniques that we learned about in the series estimation theorems. And you can even tell how good the approximation is. Another application is Euler's identity, which is widely applicable in a lot of places. You're definitely going to see that in differential equations. It's probably the lowest class that you're going to see that in, but we're actually going to prove that and show a very nice equation from it. Binomial theorem, this is something pretty cool. We'll look at it as well. I'm not going to test you on it, but I'll spend a few minutes talking about it because it's something really cool, but it is also not in our syllabus, technically speaking. And I'll also show you a few more assorted applications of Taylor series to limits, at least, as well as writing down certain numbers in an infinite sum kind of way. So that's where we are, and we're going to pick up with this example over here. So, yeah, so that's the Taylor series. There's also something else. When you plug in your x0 equals 0, the number 0 specifically, you get what's called a Maclaurin series. It's just a special case of a Taylor series. That being said, let's actually jump into the first example, which is an application of Taylor series or Maclaurin series to integrals. So A, use a Maclaurin series to compute this integral. Integral from 0 to 1 of e to the minus x squared dx. You will know at this point that there is no antiderivative of e to the minus x squared. There is no function that you can think of that you've ever seen before, where if you take its derivative, you get e to the minus x squared. So this is not something that we can do by hand using any techniques that I've shown you before, and it's not because it's hard, it's because in some sense it's literally impossible to do this. But with series we can actually do that integral. And 2, we want to approximate with a sum of 2 fractions and see how good is the approximation. Yeah, so let's start there. So, that being said, anyone wants to chime in and tell me how to do this one? Integral from 0 to 1 of e to the minus x squared dx. Okay, go. How do we do it? Yes, you can unmute yourself. Which someone should try doing. Try unmuting yourself and chiming in. Hey, all right, yes, so I hear you. So you're allowed to unmute yourself. I muted everyone because people were joining and we could hear background noise. But yeah.
So I started by writing out the Maclaurin series for e to the x.
Which is? What is it?
The summation from n equals 0 to infinity of x to the n over n factorial.
Right, so this was one of the guys. There are 4 Maclaurin series that I expect you to know. You should know what the Maclaurin series for 1 over 1 minus x is, what it is for sine of x, and what it is for cosine of x, and what it is for e to the x. Now the e to the x one is the one that comes in handy here because we have an exponential to integrate. Yeah, so you start with this, what can you do with it?
So you can substitute in wherever x is for that one with negative x squared.
Right, and remember for this one, the integral of convergence was the entire real line. So we don't even have to worry about restrictions on the x-axis. So essentially, these guys are the same because the remainder term here approaches 0, even though we never spoke about it. E to the x is this series. So if I want to find e to the minus x squared, I can just plug in minus x squared here and plug in minus x squared there, and that's the first step. So this is the summation. N goes from 0 to infinity of minus x squared to the n over n factorial dx. Right? So that would be the first step in actually using series to help you here. All right, then what?
Then I simplified it a little. I did the integral from 1 to 0 of the summation from n0 to the negative 1 to the n times x to 2n over n factorial.
Okay.
And since it's absolutely convergent, you could switch the summation.
And yeah, we're allowed to do this because of absolute convergence. If we did not have absolute convergence, that's illegal. Yeah, so the integral of that is what?
Negative 1 to the n times x to the 2n plus 1 over n factorial times 2n plus 1. From 1 to 0.
And from 1 to 0. And you can plug in 1, and then you can plug in 0. Plugging in 1, we would get just minus 1 to the n divided by n factorial 2n plus 1. And then when you plug in 0, everything dies, so that is your answer. That's the integral. Right? That's the answer. Now, the thing is, remember, there's no function that we know about that is the antiderivative of this guy. One way you can imagine this is saying that here is a series way of writing down the answer, but this series actually does not converge to the power series of any function that we know about. It's just something that we have to think about as a series. It's just an infinite sum. And there's no way to write a closed form, meaning to write it down as a non-infinite sum of any function that we're familiar with. But this is the answer, quote unquote, in general. Now, we can never actually compute what this answer is fully, but we can approximate it to within any degree of accuracy we want. And that leads us to, so that's the integral. That is the antiderivative. That is the integral from 0 to 1 of e to the minus x squared. That's what it's going to be. So, this leads to b. How would I approximate what that is using two fractions?
Given what you have in A, you can substitute in n equals 0 and n equals 1 to get your two fractions.
Right, so we have the integral from 0 to 1 of e to the minus x squared dx. This is equal to the sum, n goes from 0 to infinity, minus 1 to the n over n factorial times 2n plus 1. This is approximately equal to. Now we're just adding the first two fractions. So plugging in n equals 0, we would get 1. Minus plug in n equals 1, we would actually get a third. So 1 minus a third. 2/3 is the approximation, but as a sum of two fractions, that's going to be your answer. So using this series to approximate it with the first two terms, I would guess that the area under e to the minus x squared from 0 to 1 is roughly 2/3. That would be the approximation here. And hold on, let me check. By the way, the answer is actually 0.74 or something. So 2/3 is about 0.667. The actual answer is about 0.74. So we're a little bit under the answer, and we're off by about 0.1 something. But even that kind of leads us into part 3. So this is our approximation. I would guess that it's around 2/3, around 0.67. How would I know how good an approximation that is?
Alternating series of approximation.
Right, it's an alternating series. So by the alternating series approximation theorem, the error here is going to be less than or equal to the A sub 2 term, right? So this is the A0, that's the A1. The next term would be the A2 term. So this is your A0 term. This is your A1 term. The next term would be your A2 term. And the alternating series approximation theorem says the partial sum is actually how far that is from the actual answer is given by the magnitude of the third term here. So that's just A2, which in this case is going to be, plug in n equals 2, I would get 1 over 2 factorial times 5, which is about 1/10, which is about 0.1, which that's actually true, right? So our guess here would be 0.67. As I mentioned to you, the actual answer is, to 2 decimal places, is 0.74. Well, 0.75, which is less than 0.1 away from the actual answer, which is pretty cool, right? And by the way, for Wolfram Alpha, I think Wolfram Alpha gave me 6 decimal places here. Wolfram Alpha would have just set this an plus 1 less than or equal to 0.000.000001, and it would actually add up that many terms to get to hit its answer. So yeah. So my guess that this guy is 2/3 is actually less than 0.1 away from the actual answer, which is pretty neat. We went from a situation where we had an impossible integral, literally impossible in terms of everything we've done before series, to one that we can get within a decent approximation to the error with like adding 2 fractions, which is awesome in my opinion, but I don't know. Yeah, pretty cool. But yeah, so this is how far we're potentially away from the actual answer, and we were actually off by about 0.9, given this, given what Wolfram Alpha says. Yeah. So by the way, that is a very common problem type for us to give you some really crazy integral and ask you to use series to do it, and then use series to approximate it. So that would be like a question on its own. Yeah, it's pretty cool. I would agree. It's not everyone's cup of tea, but it's definitely useful when it comes down to actually finding some integral in real life that you care about that's just super hard. It's the hardest thing you've never seen anything that hard. Converting things to series is a pretty cool way to get to an answer. And if you have a computer to help you out, you just add up however many terms of the series you need to get the answer to within whatever desired accuracy. So that is a very cool application of Taylor series, and it's definitely one that you're going to be tested on. So for sure you need to know at minimum this application. The other applications I'm going to talk about, you're not going to be directly tested on, but I want to talk about them because they are cool, and you will find use for them in future classes. So, yeah, that's how you can use series to compute integrals. So I'll give you some time to copy that or take a snapshot. 3, 2, 1. Chicken. That was my camera thing. Let's talk about the second application, Euler's identity. So there's this really cool equation out there that says e to the I theta is equal to cosine theta plus I times sine theta, where I is the imaginary unit. So I is, by definition, it doesn't really make sense in the normal way we think about math, but it's actually pretty useful to define this. So we take the square root of minus 1 and we just define it to be this number that we call I. And it turns out that, and this is such a useful equation, you use it to prove de Moivre's theorem and all sorts of other nice things can fall out of this. But this equation actually holds true. And among the easiest ways to actually show that this is actually the case, that it's actually equal, is to use series. Now, this is something that you guys should have tried on your own. Did anyone actually try this? Anyone tried it?
I did.
You did? Did you succeed?
I think so. Yeah.
Okay. All right. What did you do?
So I did I wrote the e to the x is equal to the summation from n equals 0 to infinity of x and over n.
Right. So e to the x is equal to that. N goes from 0 to infinity. X to the n over n factorial. Okay.
And then I plugged in I theta wherever the x is.
This implies e to the I theta is just the summation, n goes from 0 to infinity, of I theta raised to the n over n factorial. Okay?
So then here I sort of like, I didn't know what to do a lot. I just started writing out terms. So I plugged in n equals 0.
Okay.
And I got 1 over 0 factorial, which is 1. Plus
N equals 1.
N equals 1, which is I theta over 1 factorial. I think it's easier to see the pattern with 1 factorial. Then I got minus theta squared over 2 factorial, because the I, when I is squared, it becomes a negative.
Okay. Let's just write out with the powers first. So it'll be this plus I cubed theta cubed over 3 factorial plus I to the 4th theta to the 4th over 4 factorial plus I to the 5th theta to the 5th over 5 factorial dot dot dot, etc. Okay. So now what were you saying?
So you can simplify like where I is squared and stuff, so the I squared becomes a negative 1. So
right, so if I is the square root of negative 1, if I square both sides, I get I squared is negative 1. So here I have I theta over 1 factorial minus theta squared over 2 factorial. What about I cubed?
I cubed becomes negative I, because you can sort of like split it up, split the 3 into like 2 and a 1. And
Yeah, so I cubed, I can think of that as I squared times I. I squared is a negative 1 and I is just I, so this is minus I theta cubed over 3 factorial. I to the fourth, well, I can think of the I to the fourth as I squared times I squared, which is minus 1 times minus 1. That gives me a plus 1. So this is plus theta to the fourth over 4 factorial. And then it just keeps starting over. So if I multiply I to the fourth by I would get I again, plus I theta to the fifth over 5 factorial. Multiply that by another I would get minus theta to the 6 over 6 factorial, dot, dot, dot. Okay, now what?
So then I group the i's and the not i's.
Right, so if you write down all the guys without the i's, we would have 1 minus theta squared over 2 factorial. Let's have colored chalk. Let's use the colored chalk. So group the guys without the i's. So it's 1 and minus theta squared over 2 factorial plus theta to the fourth over 4 factorial minus theta to the 6 over 6 factorial, dot, 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 plus, group all the guys with the i's, put them in a parentheses, and expand them. So I would get pretty much theta over 1 factorial minus theta cubed over 3 factorial plus theta to the fifth over 5 factorial, dot, dot, dot. And then?
So the green writing can simplify into cosine theta?
Yeah, that's literally the series for cosine theta. So this is actually cosine of theta. And remember the cosine we saw last time. This is cosine of theta. We saw that that was the series n goes from n equals 0 to infinity of minus 1 to the n, x to the 2, n over 2n factorial. So it's just taking on the even powers and then alternating signs. And then this guy, by the previous definition from last class, is sine of theta. So it turns out you can think of an exponential as a sum of sines and cosines, which that has all sorts of applications in complex analysis and beyond when you start to actually think about pictures in the complex plane, but I digress. That's Euler's identity. We have this equation. And you can actually use this to prove a lot of other identities. So a lot of trig identities like the, oh, this is such a useful thing. I don't even know if I want to actually go down the rabbit hole because I can actually spend like 3 more lectures talking just about ways in which we can apply this guy. But yeah, that gives us Euler's identity. By writing the exponential as a series, plugging in I theta for the x's, it turns out I can think of it as a sum of sines and cosines, where the sine is multiplied by the imaginary unit. And yeah, so that's the proof. I'll give you guys some time to write that down or take a snapshot, which is pretty cool. Now, so that proves this equation, which, by the way, now, if we plug in theta equals pi, for example. Now you can plug in anything you want here, because these guys, remember, the interval of convergence is from minus infinity to infinity. So this equation is going to be true no matter what you plug in for theta. But if you plug in theta equals pi, this means that e to the I pi is equal to cosine of pi plus I times the sine of pi. Sine of pi is 0. Cosine of pi is minus 1. And so you end up with e to the I pi plus 1 equals 0. Now this here is considered by many to be the most beautiful equation in all of mathematics. I almost forgot how to spell beautiful. Right? If you just search for like list of what are the most beautiful mathematical theorems or what are the most beautiful math equations out there, at the top of pretty much almost all of those lists will be this equation, because it talks about the most important numbers in mathematics, e pi I 1. It also includes all the important mathematical operations, addition, multiplication, exponentiation, equal. The two numbers that we use to build up the real number system, 0 and 1, are there. And yeah, e to the x, the most important function in mathematics, is kind of used here as well. It's a very short equation that includes so much math history and fundamentalism right behind it. And a lot of people really geek out about this equation. It's a really cool equation. And it's comes from Euler's, it's called Euler's identity. Now, we're going to talk about polar coordinates in this class, and that's going to, if I remember to come back and talk about this after I talk about polar coordinates, I will. But you're going to see a lot of connections here in polar coordinates as well. You can go back there, and that gives you a lot of applications as well. But that's Euler identity. Pretty cool. Gives rise to the equation that most people think is the most beautiful equation out there. And using series, it's actually not that hard to prove. Yes, the God equation. I've heard people refer it to as that as well. But yeah, really, really nice equation. Has a lot of nice things in it. Euler's identity. Here's something else. So there's also something called the binomial theorem. The binomial theorem is a theorem that tells you how to expand a binomial. So if you have x plus y raised to the n, where n is a non-negative integer, it turns out that this is actually a summation of the form k goes from 0 to n of n choose k, x to the k, y to the, do I want to do it the other way? Let's do y to the k, x to the n minus k. Sometimes you normally write it the other way around, but you'll get the same thing either way, because these guys can be swapped. You have that. Now, some of you might have seen Pascal's triangle. Does anyone actually know about that? So there's something called Pascal's triangle. It starts with a triangle of ones like that, and then you generate each new line by starting with a 1 and then adding the two guys above it and then ending with a 1. So then the next line would be 1, add these two, you get 3, add these two, you get 3, and then you end with a 1. Then 1, add these two, you get 4, add these two, you get 4, add these two, you get 6, add these two, you get 4, then you end with a 1, and so on and so forth. And you can create this triangle. Now, what's nice about this triangle is it actually tells you how to expand binomials. So, for example, if I were to have x plus y raised to the 4th power, I can think of that as x to the 4th plus 4x cubed y plus 6x squared y squared plus 4, I'm running into this guy here, 4x cubed y cubed plus y to the 4th. And you might wonder, how would you know to do that without multiplying these guys? Well, the coefficients, 1, 4, 6, 4, 1, are the same guys in the corresponding line of Pascal's triangle, right? So if I know Pascal's triangle in my head, I could be like, oh, x plus y all cubed, that's x cubed plus 3x squared y plus 3xy squared plus y cubed, right? Someone can rattle that off. And for those of you who are in my Calc 1 class, you might remember I actually gave you that identity in the final because like they wanted you to expand it or whatever. And yeah, so I just remember that in my head, but in my head I was thinking this. I didn't actually literally sit there and multiply everything out. So there's something called Pascal's triangle that allows you to get the coefficients of when you want to expand anything to an integer power, a non-negative integer power. It turns out that there's another way to generate these numbers, and it's easier in the sense that in order for me to figure out how to expand something way down in the line, like the 10th power or something, I have to go through all the previous powers and build up the triangle bigger and bigger and bigger and bigger. There's a way that I can figure out what any one line would look like without knowing what the previous lines would look like, and that is this way, and it's called the Binomial Theorem. So it coincides with using Pascal's triangle to expand a binomial. So let me show you how that's going to work. First of all, I will tell you what this symbol means. This guy, sometimes you will see him written as N, C, N, K. This guy is called a combination. You will see it in a probability class. You take a basic probability class, that guy is going to pop up. It is actually defined to be n factorial divided by k factorial times n minus k factorial, and which actually works out to be n times n minus 1 times n minus 2 dot 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 going all the way down to n minus k plus 1 divided by k factorial. Now this number is special for a number of reasons. The first reason is it tells you how many ways you can choose k things from a group of n things in no particular order. So, for example, if I asked you to find 5 choose 2, or let's go something else. Let's 10 choose 3. I can think of that as 10 times 9 times 8 divided by 3 times 2 times 1. 2 into 8 goes 4 times, 3 into 9 goes 3 times, 3 4s 12 times 10, that's 120. And that gives you this number, 120. You might say, what does that number mean? Well, basically it says, if I have 10 things, if I have 10 people, for example, in a room, and I wanted to randomly pick a group of 3 people from those 10 people, and I don't care who I pick first or second or third, the order in which I pick them does not matter. How many possible groups, how many different groups of 3 people could I have chosen from a set of 10 people? 120 groups, right? So if I have 10 people and I have to choose 3 random ones to put in a group, the number of different ways I could do that is 120 different ways, okay? So this is called a combination. This is called a combination, or it's also called n choose k for reasons I mentioned before. And you can literally type in n choose k in Wolfram Alpha and it'll actually give you an answer. You can say 10 choose 3. Type that in Wolfram Alpha, you'll get 120 as the answer. Okay. Another useful thing about this number is that it actually shows up in the binomial theorem. So, like I said, I'm erasing the notes very quickly because, again, I'm not really going to test you on this, but it's pretty cool. I just want you to see it so you can say that you've seen it before. basically what this is saying is I can write this out as n choose 0, x to the n, y to the 0, plus n choose 1, x to the 1, y to the x to the n minus 1, y to the 1, plus n choose 2, x to the n minus 2, y squared, plus dot dot dot, going all the way up to the end, n choose n, x to the n minus n, y to the n. And so, for example, if I were to take x plus y to the 6th, we saw what that was from Pascal's triangle. Now, according to the Binomial Theorem, this is going to be 6 choose 0. Oh, we did 4. We did 4 last time. 4 choose 0, x to the 4, y to the 0, plus 4 choose 1, x to the 4 minus 1, y to the 1, plus 4 choose 2, x to the 4 minus 2, y to the 2, plus 4 choose 3, x to the 4 minus 3, y to the 3, plus 4 choose 4, x to the 4 minus 4, y to the 4, right? So I start counting from 0, 1, 2, blah, 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 count all the way up to the highest power. The top number in my combination is always the highest power, it's always the 4. And then I start at the 4th power for one of the variables and count down. And I start at the 0 power for the other variable and count up. And if I were to use the formula that I gave you for each of these, you'll realize that this is actually a 1, that is actually a 4, this is actually a 6, that is actually a 4, and this is actually a 1. And ultimately that will give us 1 times x to the 4th, plus 4 times x cubed y, plus 6 times x squared y squared, plus 4 times xy cubed, plus y to the 4th. Right? And I could have done this for any positive power I wanted. So I can actually expand this binomial, right? So if I were to ask you, what is x plus y to the 6th? Well, it's 6 choose 0, x to the 6, y to the 0, 6 choose 1, x to the 6 minus 1, y to the 1, 6 choose 2, blah, 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 going all the way up to 6 choose 6, x to the 0, y to the 6. And that will actually be how we can expand this, right? And some of you might have seen that in high school, but here is something that's really cool. So here's where the cool part comes in, of how we can expand on this a little bit further. It turns out that this formula generalizes nicely for non-integer terms as well, except an infinite series is obtained. Because it turns out that if you start at a non-integer, you'll never actually, if you start counting down, you'll never actually hit 0 specifically. So there is no termination that happens, right? We normally terminate it at the n choose 0 term. But if you start at something like highest power being a half, so x plus y, say, to the 1/2. You want to look at something like that. Then it turns out you can actually think of it as a series of, say, a half choose 0, x to the 1/2, y to the 0, plus a half choose 1, x to the a half minus 1, y to the 1, and etc. And you can just keep going. And how would you actually compute 1/2 choose 1? It actually doesn't make sense in a probability interpretation, but if you had to do, basically how we do it is we'd use the other form that I gave you here. So if I wanted to do, let's see. That guy is just 1 as normal, because the number of ways you can choose 1. But the next guy, I would just take a half and multiply it by a half minus 1 and divide that by 2 factorial. Plus, and you can actually continue going on forever. So your book actually wrote this out, but the thing is, if you keep counting this down, it'll never actually hit 0. So you kind of just have to keep going, is the idea. And it turns out you can prove that this series will eventually converge to, well, the radical of x plus y. So technically there's going to be some point where you have the y to the half showing up here, but you'll have a bunch of other terms as well. And so when someone distributes a radical across a sum and they write it as x to the half y plus y to the half, what they actually did was they got this term and they got that term, but they missed an infinite number of terms beyond that, right? So didn't want to spend too much time on that, but it's really actually cool. I just want you to know about it. The binomial theorem in the integer form you should definitely know. I think most of you would have seen that in high school. If not, now you've seen it, you should actually know it. It's one of those things in higher math classes you'll be expected to know. But yeah, you can actually apply it to non-integer values. And I believe your textbook did this particular example here. So I thought that was pretty cool that I would show you. I also mentioned it to my Calc 1 class as well, that expanding a radical you need an infinite number of terms. The binomial theorem is how you would actually get to that. Lots of hand waving, but it's a cool application. So if you look at your textbook, they'll write it out a lot nicer, but I just wanted to run through that. Here's another application, limits. Example. Let's say you wanted to do that limit. Now, this is a somewhat easy limit. We know how to kind of deal with this already, but I just want to show you another way that you could look at this. So a lot of you, if you saw this limit show up on a test, probably what you do is like something like L'Hopital's rule. You'll end up having to use it 3 times. And you would eventually get to the answer that way. Now, it turns out there are other ways to do it. So for example, we can think of this limit using series. And in a lot of situations, someone like Wolfram Alpha or a computer would actually think of a limit in terms of a series. Using series instead, I can think of this as the limit as x approaches 0. And what we normally do is you can replace, because everywhere else there's a polynomial, the only guy that's not a polynomial is the sine function. What you can do is you can write the sine function as an infinite polynomial. And we know how to do that. Well, that's going to be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus dot dot dot. So you can actually replace the sine with its series. What you'll notice is going to happen is that your x's are going to cancel. And what's left over, I have a bunch of x's in the top where x cubed is the largest one, which means I can divide x cubed into everybody. So if now I divide x cubed into everybody, I get minus 1 over 3 factorial plus x squared over 5 factorial minus x to the 4th over 7 factorial plus dot dot dot. What you realize now is as x is approaching 0, that approaches 0, that approaches 0. Everyone else is going to approach 0 except that guy. So the answer is actually minus the 6th. Which is yeah, crazy, right? Series are a lot more applicable than you might think. It's not just the calculus, even though I'm showing you a lot of calculus applications. But yeah, you can do that. So that's one example. I'll give you some time to take a screenshot of that, and I'll leave you with some more examples to try by using series, and just to compare to other ways of doing it. Limit as x approaches 0 of x squared times e to the x over cosine x minus 1. Limit as x approaches 0 of cosine x minus 1 plus 1/2 x sine x over ln of 1 plus x to the 4th. Sine x minus x over 2e to the x minus 2 minus 2x minus x squared. So, not going to do those, but you can copy them down. Try them yourself. Try using series. Of course, the idea is, wherever you see an e to the x or a cosine or a sine, you're going to instead replace it with an infinite polynomial. You'll realize algebraically a lot of things are going to cancel out, and you'll be left over with something that you can just plug in the x value, which is pretty cool. It's another cool application of series, but like series are really used all over the place. It's crazy, and so I kind of rushed through these things at the end there, and definitely botched some things, but I just wanted to quickly talk about some cool applications that technically they're not in our syllabus, but it's really good if you actually know them, especially if you have to go further and do a lot of math in the future. Knowing that these techniques are out there is going to be very, very useful to you in the future. So the idea is that we can think of these functions as series, and it can help us make integration easier, can make differentiation easier, can make finding limits easier, it can make expanding things easier. I can now expand things to fractional powers where I couldn't have done that before, and it's just overall it gives you a very hefty machinery for numerical techniques. Just by thinking of things as infinite sums, it actually gives you a lot of power to do a lot of really cool mathematical manipulations with, I would say, a lot of minimal effort. And it's the kind of effort where it's easy to program a computer to get it done because it's just adding up a bunch of numbers, and the computer is very good at adding up a bunch of numbers. So there's something else I asked you guys to do a while back. So here I'm going to stop talking so much and give you guys a chance to chime in. But another application which is surprisingly useful in some situations is being able to take a random real number and write it as some sort of infinite sum. This is something I asked you guys to try a while back. Did anyone actually try it? If you actually tried it, maybe you can tell me what did you get here. So writing the tangent inverse function as a series. Did anyone try this one?
Could you rewrite the arctan as integral?
Okay, what integral?
1 over 1 plus x squared.
Okay. Now, of course, there's going to be a plus c or something here, but we'll deal with that later. Yeah? Then what?
And then you could make like minus x squared your r.
Right, so that looks like a 1 over 1 minus x, and plugging that into series form gives you what?
The sum of, like, from n0 to infinity, negative 1 to the n.
Right.
And then times x squared to the n.
Right, so it's minus x squared to the n, which you can write as negative 1 to the n, x to the 2n. And that one will even start to work conditionally at the endpoints because now it's an alternating series. Well, after we integrate. So we know that we can switch the summation and the integral as long as we're within minus 1 to 1. There's absolute convergence. You're going to see where I'm going with this in a second. So x to the 2n dx. And this is going to be equal to the sum, n goes from 0 to infinity, of minus 1 to the n, x to the 2n plus 1 divided by 2n plus 1, plus a constant. Now I can plug in x equals 0 in both sides. You will get tangent inverse of 0 is equal to the series of 0 plus c. Tangent inverse of 0 is 0, so we know that this means our c is 0. And so this means that my tangent inverse of x can be thought of as this power series. Now that guy converges absolutely for all x's between -1 and 1. He will converge conditionally for x equals -1 or x equals +1. But yeah, we have this guy here. I can think of tangent inverse as this guy within a certain window. Now, here's something that's cool. So here's the cool part. So that part is something that we've covered before. And by the way, this is a kind of example that I would expect you to know. It is a kind of question that could show up on an exam whenever we figure out what that has to look like. Like I could just ask you a problem. Hey, use a known power series to write tan inverse of x as a series. And this would be what you would have done. You'd have realized that, oh, I can think of this guy as this integral, and then I can morph that integral into a series. I can integrate it and write it as a series. If there is no way to actually connect this to a known series, how you would actually do that is the Taylor series way. Just find the nth derivative, find a formula for that, plug it into the Taylor series formula. So we have two main methods of finding a power series. One is just using some power series that we already know, and by manipulating that power series using an integral or a derivative or algebra. Another way is just use Taylor's formula. And lucky us, we're in Calculus 2 where every function we've ever seen is infinitely differentiable. So we'll always be able to actually construct something like this. So here's the cool part. So we know that tangent inverse of x can be expressed as this series on the closed interval from -1 to 1, where at the endpoints it will converge conditionally, but it will converge absolutely in the open interval, right? Now, here's what I would suggest. Plug in x equals 1 into this equation. If I plug in x equals 1, what does the left side become?
Wouldn't that be pi over 4?
That gives you pi over 4. And the right side is going to be a series. -1 to the n over 2n plus 1. In other words, I can start to write out some terms here. Plug in n equals 0, I get 1. Plug in n equals 1, I get -1/3. Plug in n equals 2, I get +1/5. Plugging in n equals 3, I get -1/7. Plug in n equals 4, I get +1/9 minus ... In other words, I would like you to appreciate what we've just accomplished. We took the real number pi, and I could write this as, well, 4 times everything over there. It's 4 minus 4/3 plus 4/5 minus 4/7 plus 4/9 minus ... And it turns out that that guy is going to converge to pi. It'll actually converge to 3.1415926. That is pi. I can actually write this real number as an infinite sum, which might be convenient for what yo again. Yeah, yo. Right, so some of you might have seen this every now and then. I don't know, maybe you guys aren't as weird as I am and look up Google map things randomly at sometimes. But you'll sometimes see people, it's like, oh yeah, well we can think of pi squared as this infinite sum, and therefore they use this in a proof to do something else. And you're like, where did they get that equation from? Why would anyone know that? And this is how someone would know that. And this is just one way to express pi as an infinite sum. There are many, many other ways, just if I use another formula. Like if I used, say, a sine inverse, I could get to pi in another way. Or use some other function, I can get to pi in another way. But it's actually pretty cool that I could actually write down, I can take a real number and I can dissect it into an infinite sum, which can be convenient from time to time. As you've seen, infinite sums are convenient from time to time. So pi is actually also that guy. And you'll notice that there is a pattern here. The denominators are just all the odd integers. The numerators are always 4. And then your alternating signs. So one way to think of pi is 4 over 1 minus 4 over 3 plus 4 over 5 minus 4 over 7 plus 4 over 9 minus 4 over 11 plus 4 over 13 ad infinitum. Yeah, so I don't know. I think that's pretty cool, and yeah, that's just another use of series. To infinitely expand something, which on one hand it looks like I'm getting something more complicated, but on the other hand, computationally speaking, the right side here is more simpler than the left side. The left side is just a symbol. Who the heck knows what that means, really? Like, what's an intuitive feel for this number, the ratio of a circumference to the diameter of a circle? Sure, but mathematically, that's kind of a lacking definition. It's actually this sum, and I can write it in as many other sums as well. And it's kind of strange that I can add up an infinite number of rational things and end up with something irrational, but we also saw that minus ln2 also was a sum of rational functions. Rational numbers. Yeah, and I think that is it. So this ends, let me check my notes all the way over here. Yeah, so this ends 10.10. So again, I'll reiterate, the only thing you must know here how to compute and approximate integrals. So like the first example, so I can give you an integral, the integral from 0 to 1 of e to the minus x squared dx. And I want you to know how to compute it as a series, how to use a finite number of terms to approximate what that series would add up to, and have some reasoning for why you would know how to get how good an approximation is. Like the alternating series approximation theorem is a very common one. And once you have an alternating series, you can apply that. The rest was for fun. So I'll never outright test you on it. I might ask you a bonus problem on it if the opportunity arises, but I'm not really going to test you on the rest of it. However, it's actually constructive fun depending on the future path that you guys might take. So for those of you who are going on to some serious mathematics in the future, the stuff that I mentioned is going to come back and will be useful in the future. But I suppose not for everyone. So you can consider the rest for fun, but this part, how to compute an integral and approximate it and tell me how good the approximation is, that you need to know. That you will be tested on for sure. It's for sure coming up on your final, and it's for sure something that I would ask you in an actual test. Yeah. But that actually ends chapter 10. Any other?
Same thing for like E, right? Like.
Yeah, you could do the same thing for like E. So if you wanted to write So we know that e to the x is the sum of x to the n over n factorial, n equals 0 to infinity. Well, that's just 1 plus x squared over 2 plus x cubed over 3 factorial plus x fourth over 4 factorial plus da da da. So I can actually find e by plugging in x equals 1. Plug in x equals 1 here, plug in x equals 1 here, and that's just going to give me 1 plus 1 plus a half plus a third plus a sixth plus 1/24 plus 1 over 120 plus, right, and we know that this here is 2, right, so it's 2 plus a bunch of things. So we know that e is 2.71828, etc. So it turns out that I know for a fact that this sum here converges to a number, a half plus a third plus a sixth plus a 24 plus a blah blah blah. It converges to 0.71828 blah blah blah. Yeah, so I can write e as an infinite sum. That might be useful. And so if I wanted to approximate e to a certain number of decimal places, what I could do is I could just tell a computer that that's e. Whenever a user types in e, think of it as this thing. And if they want an answer to 15 decimal places, just use this approximation theorem to tell you how many of these numbers you need to add up. Right? So we don't have to be the old school way like Euler trying to figure out what e is using a compound interest kind of idea. We can literally just use an infinite sum. Add up how many terms we need to get a tolerance we want, and Bob's your uncle. Yeah. So yes, you can do it with e, you can do it with almost any real number. We saw how to do it with ln2 last class. Yeah, lots of stuff. Which, by the way, I did the alternating harmonic adding up to minus ln2 in the G8 section. I like the way I did it there better. So you could look up that lecture if you wanted. But that ends chapter 10. Any general questions, concerns about chapter 10 material? So the next thing we're going to do is chapter 11, but of course with 10 minutes left, I'm not sure exactly if that's going to be worth starting at the moment. So yes, we are going to learn vector and stuff. That comes later on. So what we're going to do next is we're going to talk about the idea of parametric curves, parametric equations. Then we're going to go into polar coordinates. Then we're going to start talking about the vector stuff. So parametric equations, we'll cover that on Tuesday. So like I said, technically it's not an official class date, but I'll be here recording a video, and I'd love if you guys can join me, but it's not required. And I'd probably also start polar coordinates on that class lecture, but it'll probably spill over into Thursday's lecture. Then by the next class, we'll start the vector stuff. So vector stuff is coming 3 classes from now.
Wait, so just to reiterate, like next week's just normal. We're just like ignoring what they're saying. The week after, we treat it like break, right?
Yes, spring break would normally be the week following, I think.
Okay.
Yeah.
So we're not going to have class from April 8 to April 16?
Correct. And April 7th, I'm keeping that as a Wednesday schedule. So April 7th, we will not have class. I'll have class with my GH section. Yeah, so like I said, I'm continuing to have regular classes right up until April 8th. April 8th to the 16th, no classes. April 7th, there's no class because it's a Wednesday schedule. Yes, I'll still give you 2 in-class exams. That's the plan. But for this weekend, I'll only post a mock exam. So you'll get a mock version of what your exam 1 would have looked like. And I'll post that either Friday or Saturday for you to go through. Yeah. Yeah, so the first exam is covering everything up to series. So everything up to the end of chapter 10 is exam 1, and then literally everything after that is exam 2. So exam 2 is going to cover all the vector, calc 3 stuff, and polar coordinates. Yeah, so the practice exam by tomorrow evening, latest Saturday morning, I will post that. But it's a mock exam, so I'll give you a mock exam. You'll take it pretend it's a real exam and try it just to kind of see where you are, what you understand, what you don't understand, so that by the time the real exams come around, you'll kind of know where you are. Yeah, the department needs to agree on how the exam will actually be administered. So I have my own ideas of how I want to do it, but I can't really do it without special permission. Yes, the YouTube video of this will be up by tomorrow, and I can also I keep forgetting to send the links for the Zoom things. I should kind of set it up to send out the link automatically to whoever registered for the class. I don't know if I can actually do that. But yeah, you'll have access to both. So I'll post this. I think this should be up by late tonight. But yeah, it'll definitely be, the video here will definitely be on YouTube by tomorrow. I will resend the link for office hours. I sent it like a while ago. I think the same link is going to work currently. Yes, I'll send whatever links to the previous versions of the class in Zoom. I've been consistently posting on YouTube, which for what I write on the board, I think the YouTube videos are actually better. You'll see better quality there. But in the Zoom version, you'll also have access to the chat window that I'm looking at, and you'll probably hear people who are asking me questions better in that version. So the audio might be better in the Zoom version for you, while the video is better in the YouTube version. This is lecture 17. Yeah, so definitely the YouTube is better for the visual quality. But I'll also provide you links to the Zoom version. Yeah, well, I think we're not doing quizzes anymore, but I will give you opportunity for bonus later whenever possible. Yes. So I'll definitely make up for it somehow. So yeah, as I mentioned, it's a crazy time for everyone. I definitely do not have any intentions of making your lives harder here. So it's definitely going to be So if you had opportunity to get bonus before, I'll figure out a way for you to have that opportunity now, and your testing will be given under fair conditions and all that good stuff. No, I won't do an online quiz to replace actual in-class quizzes. I don't think that works. I don't know if I'm going to teach Calc 3 next semester. So the City College Math Department is weird in that they don't really tell us what we're teaching until like a week or two before classes start. Like I didn't even know that I was teaching Calc 2 until like 3 days before the class started. It was crazy. They usually tell me late. Like at other colleges, I know what I have like a year in advance. Like I already know what I'm teaching next summer at my other colleges, but yeah, City College, they tell you very late. So I don't know what I'm teaching in the summer or fall. I have no idea. So I definitely want to do Calc 3 because I don't have any YouTube videos up for the new Calc 3, so I want to do that and I'll definitely ask for it, but I do not know that I will get that for sure. Okay, would summer classes have a distance learning component? For sure, that will be the case at the other college I'm teaching. So they said that. For City College, I don't know. But I wouldn't be surprised if this continues throughout the end of summer. I wouldn't be surprised by it. But there's no word about that in CUNY, as far as I know. Oh, the whole year would be online? I might have missed an email that said that, but I don't know. I'm 99% sure that they would continue this through the summer. Would it continue through in the fall? I don't even know. Okay, so I do have some people saying that fall 2020 would also be online, but I didn't see that. Like I'm so overwhelmed with emails, sometimes I just start ignoring them after a while. I really need to catch up on it, yeah. Yeah, anything else about this class? Well, yeah, maybe I should wear a mask, but really I'm the only one here. Like, there's no one else around. And I saw the custodians and everything, they wiped everything down. They disinfected, like, everything. So, and I still have, like, wipes and hand sanitizers with me, but, yeah. Anyway, I think we'll start wrapping up. We're pretty much coming on time. Yeah, so if that's that. And of course, if you have any concerns, you can just shoot me an email. And if I don't send you guys the Zoom links by tonight, someone can email me and remind me. I'll be sure to send those out. I keep forgetting to do it. So I think when it comes to a study guide, I think the mock test would be the best study guide because I would make it very similar to the mock test I'm giving you. Yeah, so I'll also put a small review on the website, but the mock test would be the best review for whatever the legitimate test one is. I'm not going to make it different.
How about the Pearson?
What about the Pearson? So online homework is continued as normal.
You didn't post any homework till like last week, I think. I think it was up to like 10.6, I think. Then you didn't post any.
Yeah, I actually updated the homework like 15 minutes before this class, so it's updated now. So homeworks for up to 10.10 is up, and I believe I also posted homework for 11.1 and 11.3. So from sections 10.5 to 10.10, I pushed that to be due on April 11th, and then 11.1 and 11.3, which we'll cover next week, that's due on April 18th. So I actually updated the homework like a few minutes before this class. So you should see more homework there.
Also, is there any way like we can go back to the homework so we can study from it? Because after you've done the homework, you cannot go back to this question that you did it for the homework. Is there any way you can go back to the question?
Yes, there should be a way. I think it's set up to automatically allow you to view the homework that you've already done, provided that you opened it before the due date. So if you totally missed the homework and you never clicked on it, then after the due date you won't be able to open it. But I believe if you started it, you should be able to.
No, I actually did the homework, but after his due date, I was trying to go back to it, but I couldn't because he didn't let me. It was like only like 2 or 3 topics that I can go back. But from like topic like from 7 point, like the integral stuff, I couldn't go back to this question.
Oh, that's strange. Maybe email me, because that should not be the case. You should be able to review all past homeworks for sure. But there were a few homework assignments that were due last week that I actually extended them to the 11th. But yeah, anyone who's having trouble viewing past homework, just let me know, and I'll try to fix it.
So we're only doing like 11.1 and 11.3, then moving on to 12?
Yes.
Okay.
So 11.1 is just general things about parametric curves. 11.3 is polar coordinates, and then we're going to jump into chapter 12, which is 3D vector stuff. Okay, so hopefully that answers all the important questions. So testing, just to review, from what I covered today, the most important thing is to know how to construct a Taylor series, to know how to use Taylor series to approximate integrals, and to estimate them with a finite number of things. Class will continue as normal next week, but from the 8th to the 6th,
16th, I think.
from the 8th to the 16th, we're not doing anything. And quizzes are pretty much not happening anymore, but I'll give you opportunities for bonus otherwise, and I'll post mock quizzes. Mock tests will be posted today, tomorrow night to Friday, Saturday morning, and that would be the best review for the actual first test whenever the department tells me what's going on there. Oh, yeah, and I see people giving some helpful comments on how to review homework problems. So, okay, so I'm going to stop recording, stop now, and all right, you guys have a good night, stay safe, keep working hard, and that's it. Email me with any issues, concerns, and I'll get back to you guys. So.